This is a video containing an introduction and explanation of combinatorial proofs. Towards the end of the video, there's a series of examples which become progressively more difficult as they go on. First, we will start with a very introductory example just to explain the basics of a combinatorial proof. This video was presented by and created by a group B14, which includes members TJ Bearse, Matthew Berger, Zach Huston, and Ryan Kreiter. This video can also be viewed on knoatom.com. First, we'll start with an overview of exactly what the nature of a combinatorial proof. This will include a definition and the various advantages and disadvantages that are present within the combinatorial proof method. First, a combinatorial proof is established through proving the equivalence of two counting expressions exclusively with counting principles. And second, essentially two different stories which can arrive at the same conclusion. In this way, it's a less formal method of proving but still equally valid. And third, this proof method allows us to look at an equation differently rather than relying solely on algebra. The structure of combinatorial proof is given in four different steps. First, define the set S. The set S is the possible outcomes that you are choosing from or counting from the total set or total universe. Second, show that the cardinality of this set S is equivalent to N by counting one way. Third, show that the cardinality of S is equivalent to N by counting in a different alternative way. And finally, fourth, conclude that the results given by step 2 and step 3, that N is equivalent to M. Our first example is very basic in that it is given the understructure and underpinnings of the combinatorial proof method. First, our goal is to prove that choosing k from n elements is equivalent to choosing n minus k from n elements. Consider a scenario where you have n different competitors. Of these competitors, k must win the competition. We will define set S as all winners within the competition. The first route, or the first option, or the first story that we are looking to tell in the terms of a combinatorial proof is just simply choose k from n. We need to choose k winners from n people. And this is the setting that if you have a certain number of racers, a certain number of them will place, and those that you choose are the winners. In route 2, choosing k winners is the same as choosing n minus k losers because they are complements within the universe of competitors. That is, choose n minus k from n. In this way, you can think of choosing the set of losers. If you choose the set of losers, then it also implies that the rest of the remaining will be the set of winners. In this way, choosing the two is equivalent to each other and therefore concludes the combinatorial proof in the basic sense. We counted the same thing in two ways, therefore these expressions must be equal, assuming that the values of both n and k are equivalent as well. Example 2. Prove that choosing k from n elements is equivalent to choosing k minus 1 elements from n minus 1 elements plus choosing k from n minus 1 elements. The scenario we are going to discuss is a March Madness style scenario where k teams are in places in a bracket out of a total n teams. The n teams in the March Madness context is thought of as the number of Division I teams, whereas the bracket is the NCAA tournament at the end of the year where there will typically be 64 teams. S will be the set of all possible teams to play in the tournament, that is, choosing a set of S from the possible number of Division I teams, the top 64 teams will play in the tournament. Route 1A. The first way can be counted by considering the situation in which a certain team is within the bracket and the situation in which a team is not within the bracket. In the first case, the number of teams is reduced by 1, as is the number of remaining bracket places in the tournament. This is true because once the team is in the bracket, they are no longer in the total pool. At the same time, once they are placed in the bracket, there is one less place to be selected. This can be given as choose k minus 1 from n minus 1 elements. The k minus 1 portion of this piece of the equation comes because now there is one less slot in the bracket. In the NCAA bracket, there are only 63 slots left. The n-1 means that there is one less Division I team competing for the other 64 slots simply because the team in question has already been selected as a part of the bracket. In the second situation, the team is not picked as part of the bracket pool. At this point, the number of total options to be placed into the bracket is reduced by 1. This leaves us with n-1. While the positions in the bracket itself remain the same, this is still k. Therefore, choose k from n-1. In this way, in the NCAA context, there are still 64 slots to be chosen, and there is one less team in the total pool of Division I teams within the NCAA because the team did not make it into the bracket. When these two situations are combined, there is the case where the team in question makes the bracket and the case where the team does not make the bracket, and the result from this is choose k-1 elements from n-1 elements, and then add choosing k elements from n-1 elements. Route 2. Route 2 is straightforward. In this situation, there are n teams. This includes the team in question, trying out for the k spots in the bracket. This can be given as choose k from n, and this would be the 64 slots in the tournament from the n, the total number of Division I teams. Because we counted the same scenario in two different ways, then these ways must be equivalent. That is, choose k from n elements is equivalent to choose k from n-1 elements plus choose k-1 from n-1 elements. Checking combinatorial proofs. Combinatorial proofs come with their own version of error through miscounting. The proof can be checked by running through each side of the equation. For example, in the case of a proof of Pascal's theory, choosing k from n elements is basic enough going through the definition of a combination. However, the second half of the equation is more complex. The second aspect, choose k-1 elements from n-1 elements plus k from n-1 elements, is much less straightforward. It can be thought of as the union between two disjoint sets. Let set A be equivalent to the first side of the equation, that is, choosing k-1 from n-1 elements. In this case, set A represents the situation in which the team in question does make the bracket. Then let set B be the situation where the team does not make the bracket, that is, choosing k from n-1 elements. In this situation, it's the case where the team does make the bracket and the situation where the team does not make the bracket are disjoint. That is, no members of the set, no members are counted twice through the situation. And therefore, the union of these two will result in where the situations where both the team is and is not in the set. At this point, is it equivalent to the choose k from n because you are choosing all situations in both instances. And our third example is more difficult, given to explain the power of a combinatorial proof. Prove that the summation from I equals 0 to k, choosing I from m and choosing k minus I from n minus m elements is equivalent to choosing k from n elements. Consider a university, much like the University of Michigan, where n students have a unique student number from 0 to n. We want to choose k students to expel. The first route is thought of in this situations. Each set of students has a largest student ID, j. First, find the number of sets with largest ID, j. J's in the set are so that there are k-1 to choose. Because j is the largest, we choose from j-1 elements. Now sum all these sets that have j as the largest element for all j. That is, the sum from j equals 1 to k for choosing k-1 to j-1. In this way, the summation goes through the various elements in which a certain number is the maximum element, and then it sums all combinations in which that element is true. As it goes through the list of unique names for the University of Michigan, it will sum all totals where there is a certain unique name as the largest number. As it goes through, it will reach every unique combination of elements. And the second route is before and just as simple. It's n choose k. That is choose k from a total of n elements. Finding a combinatorial proof is often difficult. The approach to solving the proof is sometimes not immediately obvious. In the case where it is not obvious, there are some steps which make solving a problem much clearer. First, the goal is to make certain that you identify exactly what S is. That is, what are the possible set combinations to choose from. In the first example, you could look at S in two different ways. S was the total number, or you could look at S in one way, but approach it in two different ways. The first was choose it as the number of winners, and the second is choose it as the number of losers. In each instance, the values n and m through each combinatorial method or combinatorial approach resulted in the same S. And second, start with the simpler side, identify exactly what it is asking. In this way, you can look to example 2, the topic talking about Pascal's identity. The Pascal's identity approach is started with a simple choose k from n elements. In choosing k from n elements, you can split this up into two different ways. The point where you have a certain element that was chosen, or the part where you have a certain element that was not chosen. In the NCAA example, you have the part where it was chosen, in the case of where it was part of the bracket. And in this situation, the total number of elements to choose from was reduced from 1, as was the number of elements that you are actually physically choosing. In the second case, you can split it up into the case where it was not part of the bracket. At this point, when it is not part of the bracket, then it is that you choose n minus 1 elements because you have one less, but the bracket slots remain the same. That is, there is still k slots in the bracket. The point of this example and the application to finding combinatorial proof is that if you start with a simpler example, that you can break it down into other forms. And by breaking it down into other forms, it sometimes makes clear exactly what the other side is asking and how it is related to the simpler, more clear form. And again, you can find this video at konatom.com. That is konatom.com.